Hello everyone and welcome. I'm excited to kick off today's presentation on motion. This is the first slide, so I just want to start by saying how glad I am to have you all here. We'll be exploring the fascinating world of motion, its principles, and how it impacts our daily lives. Over the next few slides, we'll cover key concepts, examples, and maybe even some new insights. So let's get started and enjoy the journey together. Let's take a closer look at some key concepts related to motion. First, we'll visualize motion through a distance-time graph, which helps us understand how far an object has traveled over a period of time. Moving on, the idea of average velocity is essential because it gives us a sense of how quickly an object is moving overall, even if its speed varies during the journey. We also need to consider non-uniform circular motion, where an object moves along a circular path but at changing speeds, contrasting with uniform circular motion, where the speed remains constant. This brings us to non-uniform motion in general, highlighting how the rate of change can vary. Next, let's discuss magnitude, which refers to the size or amount of a quantity, such as speed or force. Understanding how displacement is defined is crucial, because it measures the shortest straight-line distance from an initial point to a final point, regardless of the actual path taken. Acceleration is another fundamental concept. It's the rate at which velocity changes over time. Similarly, average speed provides an overall measure of how fast something travels, regardless of direction. When we talk about uniform circular motion, the object moves at a constant speed along a circular path, which is different from uniform motion, where the object moves at a constant speed in a straight line. The velocity time graph is useful because it shows how velocity changes over time, helping us analyze acceleration. Distinguishing between distance and displacement is important. Distance is the total length traveled, while displacement is the straight line difference between start and end points. We'll also look into what distance really means in a physics context, as well as uniform acceleration, where the acceleration remains constant over time. In the conclusion, we'll tie everything together, emphasizing the importance of understanding these concepts to analyze different types of motion effectively. Finally, we'll compare uniform motion and non-uniform motion in a table, highlighting their differences in terms of acceleration, velocity, and overall behavior. We'll explore some practical examples of distance and displacement, and clarify what rectilinear motion is, motion along a straight line. Understanding how time, average speed, and velocity relate helps us interpret motion more comprehensively. We'll also review the displacement formula, which is fundamental in calculations, and the importance of the reference point and reference frame in defining motion. By connecting these ideas, we build a solid foundation for analyzing how objects move in various scenarios. Imagine you're inside a bus, and you see other passengers just sitting quietly, seemingly at rest. But from an outside observer watching the bus pass by, those same passengers are clearly in motion. This highlights an important idea. To describe movement accurately, we need a common reference point or a frame of reference. Without this shared point, it's difficult to tell if an object is moving or stationary. That's why we introduce the concepts of a reference point and a reference frame. A reference point is simply a specific spot we choose to measure from. The reference frame is the entire perspective or coordinate system that uses that point as a basis for describing positions and movements. Now here's a key insight. An object may appear to be moving to one observer but completely stationary to another, depending on their reference frame. For example, if you're on a train, you might see the trees outside moving past you, but someone standing on the platform sees the train moving. So, whenever we analyze motion, it's essential that all objects we consider are described within the same reference frame. This ensures our observations are consistent and meaningful. By establishing a clear reference point and frame, we can accurately describe the position and motion of objects relative to each other. Let's talk about the concepts of distance and displacement. The magnitude of the length covered by a moving object is called distance. Think of it as the total path the object travels, and importantly, it has no specific direction. Now, displacement is a different idea. It's the shortest straight line distance between the starting point and the final position. Displacement not only has magnitude but also a direction, which makes it a vector quantity. An interesting point to remember is that displacement can be zero if an object returns to its starting point, but the distance traveled will always be a positive value and cannot be zero unless the object didn't move at all. These concepts are fundamental because they help us understand how objects move and how to measure that movement accurately. Throughout this presentation, we'll see how these ideas are key to analyzing motion in different scenarios. Let's take a look at the distance formula. Delta equals d1 plus d2. In this example, the total distance traveled is 4 meters plus 3 meters plus 5 meters, which adds up to 12 meters. Now, it's important to remember that distance here refers to the total movement of an object, regardless of the direction it moves in. It simply measures how much ground the object has covered from start to finish. So, when we talk about distance, we're focusing on the overall ground covered, no matter where the object begins or ends. This concept is fundamental because it helps us understand the total movement without getting into the specifics of direction, which will be useful as we explore other aspects of motion. So, for example, if an object moves from position A to position B, then its position has changed. And this change in position is what we call displacement. Displacement is essentially a measure of how far and in which direction an object has moved from its starting point. It's important to note that displacement is a vector quantity, which means it has both a magnitude, how much it has changed, and a direction. We often represent this with an arrow that points from the initial position to the final position. This helps us visualize the shortest path between the starting and ending points, regardless of the actual path taken. Understanding displacement is crucial because it gives us a clear way to describe an object's overall change in position, which ties into the larger theme of motion and how we analyze movement in physics. All right, let's take a closer look at the displacement formula. Displacement, which we write as deltax, is simply the difference between the final position, xf, and the initial position, x0. Think of it as how far an object has moved from its starting point to its ending point. The final position, xf, tells us where the object ends up, while the initial position, x0, is where it started. The displacement, deltax, captures the overall change in position, regardless of the path taken. This formula is fundamental because it helps us understand how far and in what direction an object has moved. It's a key concept that connects to the overall theme of describing motion in physics. So, whenever you're analyzing movement, remember, displacement is all about the difference between where you began and where you ended up. Let's walk through how to calculate displacement, which we'll refer to as d first. Recall that displacement is the difference between the final and initial positions. In this case, John starts at positions I, which we set at 0 for simplicity. Then, he travels 250 miles to the north, so his final position before backtracking is 250 miles north. However, he then goes back 105 miles south to pick up his friend. To find his overall displacement, we subtract the southward distance from the northward distance. So, 250 miles north minus 105 miles south gives us a net displacement of 145 miles north. This is how we arrive at the calculation d equals xf minus psi, which in this case equals 250 minus 105, resulting in 145 miles north. It's important to note that displacement considers only the starting and ending points, not the total distance traveled. Let's walk through how we apply the Pythagorean theorem to find the displacement. We start with the formula. AF squared equals AH squared plus HF squared. Now, when we substitute the values, since AH is half of 4 km, that's 0.5 times 4, which gives us 2 km. Similarly, HF is half of 3 km, so 0.5 times 3, giving us 1.5 km. Squaring these, we get 4 and 2.25, and summing them up gives us 6.25. Taking the square root of 6.25, we find that AF equals 2.5 km. So the magnitude of the displacement from point A to point F is 2.5 km. Remember, the initial point is A and the final point is F, so the displacement is essentially the straight line distance between these points. To calculate this, we use the right triangle AHF, which is shown in the figure. This helps us see that the shortest path, our displacement, is 2.5 km. Now moving on to the total distance covered, we add up each segment along the path, OB, BC, CD, DE, and EF. Using the grid, each side of the square tiles measures 0.5 km, so we multiply accordingly. 3 km for OB, 1 km for BC, 1.5 km for CD, 0.5 km for DE, and 0.5 km for EF. Adding all these up gives us a total distance traveled of 6.5 km. To sum up, the key points here are that the total distance covered is 6.5 km, which is the actual length of the path taken, and the displacement, our straight line measure from start to finish, is 2.5 km. This illustrates the difference between the total path length and the shortest possible straight line distance, which ties into our overall theme of understanding motion and displacement. Let's talk about magnitude, which is a fundamental concept in physics. Magnitude refers to the size or extent of a physical quantity. Think of it as how big or how much of something there is without considering the direction. Now, when we look at quantities like velocity, displacement, weight, momentum, force, or acceleration, these are examples of vector quantities. They have both magnitude and direction, which makes them a bit more complex but also more descriptive of real-world situations. On the other hand, scalar quantities are simpler because they only have magnitude. Examples include time, distance, mass, temperature, area, and volume. These are straightforward. They tell us how much of something there is, but not where it is or which way it's moving. Understanding the difference between scalar and vector quantities and the concept of magnitude helps us describe physical phenomena more accurately. It's a key part of analyzing motion and forces in physics, tying into the overall theme of understanding how things move and interact in our physical world. Let's talk about speed. Speed is defined as the ratio of distance to time, meaning how much ground an object covers over a certain period. When we talk about average speed, we're essentially looking at the total distance traveled divided by the total time taken. This gives us a useful overall measure of how fast an object is moving during a journey. Speed is fundamentally the rate at which distance changes. So, if a body covers a specific distance in a given amount of time, its speed can be calculated using this simple formula. Now, moving on to the concept of time, it's the duration of an event, usually expressed in seconds. Time is everywhere in physics because most phenomena happen over a period of time. And importantly, time is a scalar quantity, which means it has magnitude but no direction. Connecting this to our overall theme, understanding how time relates to speed helps us analyze motion more comprehensively. Whether we're calculating average speed or understanding how quickly something changes position, time is always a key factor to consider. Now let's talk about non-uniform motion. When an object covers unequal distances in equal intervals of time, we say it's in non-uniform motion. This means the speed isn't constant, and the object may be speeding up or slowing down. On the other hand, when an object covers equal distances in equal intervals of time, it's in uniform motion. This indicates a constant speed, making its motion steady and predictable. Recognizing the difference between these two types of motion helps us understand how objects move in different situations. As we go further, we'll explore how these concepts apply in real-world scenarios and their significance in understanding motion overall. Let's take a closer look at what we mean by uniform motion. Essentially, this type of motion involves an object moving in a straight line, with its velocity staying constant throughout the journey. That means, as it covers equal distances, it does so in equal intervals of time. And interestingly, this doesn't depend on how long the overall motion lasts. What matters is that the speed remains steady during the movement. This concept is fundamental because it helps us understand motion in a very predictable way. When an object is in uniform motion, we can easily calculate how far it travels over a given period, making it a key idea in the broader study of kinematics. So, in the context of our presentation, uniform motion serves as a perfect baseline for understanding more complex movements. Let's take a look at the movement of the blades of a ceiling fan. Now, imagine the blades spinning around. If we think about the speed of a car, for example, if it's moving at 10 meters per second, that means it covers 10 meters every single second. The key thing here is that the speed remains constant during each second. This concept is a perfect example of uniform motion, where the object moves at a steady, unchanging speed. So, when we see the fan blades spinning smoothly without speeding up or slowing down, they are demonstrating uniform motion. Understanding this helps us see how objects can move consistently over time, which is a fundamental idea in physics. It also connects to the bigger picture of how motion works in everyday life, from cars on the road to spinning fan blades. Let's talk about non-uniform motion. So this type of motion is defined as the motion of an object where it travels with varied speed. That means the object doesn't move at a constant pace throughout its journey. Importantly, it doesn't cover the same distance in equal time intervals, no matter how long those intervals are. This is a key point because it highlights that the speed isn't constant. Instead, it changes from moment to moment. Understanding this helps us see how objects can move unpredictably or irregularly, which is quite common in real-world scenarios. So, when analyzing motion, recognizing non-uniform motion is crucial because it requires different methods to measure and describe the movement compared to uniform motion. When we talk about motion along a straight line, or what we call linear motion, we're essentially describing a scenario where only one coordinate axis, along with time, is needed to specify the particle's position. Think of it as tracking something moving back and forth along a single path. Some common examples are a parade of soldiers marching in a straight line, or a train moving smoothly along a straight track. These are classic examples where the motion is confined to a single dimension, making analysis simpler. Understanding this concept helps us get a clearer picture of how objects move when their motion can be described along just one axis, which is fundamental in studying more complex types of motion later on. This type of motion is seen if an object is traveling at a constant speed around a fixed axis or center point. It's a situation where the object moves along a curved path, but what's important is that it maintains a constant radial distance from that center point at all times. In other words, it stays the same distance away from the center throughout its movement. Additionally, as it moves along this curved path, its direction at any moment is tangent to that path. So even though the speed is constant, the direction is constantly changing, which is a key characteristic of uniform circular motion. This concept ties into our overall discussion of motion because it illustrates how objects can move in predictable, circular patterns while maintaining consistent speed, highlighting the interplay between speed, direction, and force in circular dynamics. This type of motion is inconsistent because if an object is traveling at a variable angular speed around a fixed axis or center point, then the motion of that object is said to be inconsistent. This is because it covers a curved path, which naturally introduces some variability in its motion. Additionally, it will experience a variable radial acceleration, meaning that its velocity would change every second. So, in essence, whenever the angular speed isn't constant, the motion becomes non-uniform, highlighting the dynamic and changing nature of such circular motion. The rate of change of displacement is known as velocity. Now, what's important to remember here is that velocity is a vector quantity, which means it has both magnitude and direction. When we talk about velocity, we're not just interested in how fast an object is moving, but also in the direction it's moving in. For example, if a car is moving north at a certain speed, that's its velocity. Now, to understand how velocity is calculated, we can look at the simple formula. Velocity equals displacement divided by time. Essentially, this tells us that velocity is how much an object's position changes over a specific period. So, in summary, velocity gives us a complete picture of an object's motion, combining both how fast it moves and where it's headed. This concept ties into the overall theme of understanding motion in a more detailed way beyond just speed. Speed is a scalar quantity, which means it has no direction attached to it. It simply tells us how fast an object is moving. When we say the speed of a particle is high, it means the particle is moving quickly. Conversely, if the speed is low, the particle is moving slowly. This concept is important because it helps us understand the rate of motion without worrying about which way the object is headed. Remember, speed gives us a clear measure of the particle's pace, and it's a fundamental idea when analyzing motion in physics. Let's look at solution 1. We know that the basic formula for distance is distance equals speed times time. So in this case, Rahul drove for 2 hours at 60 km/h. That means the distance covered in those 2 hours is 2 times 60, which equals 120 km. Then, he continued for another 3 hours at a slightly higher speed of 70 km/h. So in those 3 hours, he covered 3 times 70, which is 210 km. Adding those distances together, the total distance Rahul traveled is 120 plus 210, giving us 330 km. The total time he spent driving was 2 hours plus 3 hours, so that's 5 hours in total. Now, when we talk about average speed, especially over a journey like this, it's important to understand that it's not just the simple average of the two speeds. Instead, the average speed is calculated by dividing the total distance traveled by the total time taken. So in this case, the average speed of Rahul's trip from Pune to Nagpur is the total distance, 330 km, divided by the total time, 5 hours. This concept is crucial because it helps us understand the overall pace of a journey, regardless of how the speed might have varied during different segments. And that leads us to our key point. The average speed over a period is essentially the total distance covered divided by the total time taken. This idea applies broadly, whether we're talking about vehicles, objects, or any moving body. Let's look at the solution step by step. The initial distance traveled by the person, which we'll call I, is 7 meters. The final distance traveled, XF, is 18 meters. Now for the time intervals, the initial time, T, is 4 seconds, and the final time, TF, is 6 seconds. The question is, how do we find the average velocity during these periods? Well, the key concept here is that average velocity is basically the total displacement divided by the total time taken. So in this case, the displacement is the change in position, which is XF minus I, and the total time is TF minus T. Remember, average velocity gives us an overall idea of how fast and in which direction the person is moving during that time interval. When we calculate it, we take the total change in position, which is 18 meters minus 7 meters, giving us 11 meters, and divide that by the total time, which is 6 seconds minus 4 seconds, or 2 seconds. This calculation will give us the average velocity over that specific period. It's a simple but powerful way to understand motion, especially when the velocity isn't constant, because it gives us the overall rate of change of position over the time interval. Acceleration is essentially the rate at which velocity changes over time. When you think about it, it's how quickly something speeds up or slows down. The key formula here is that acceleration equals the change in velocity divided by the time it takes for that change to happen. It's important to remember that acceleration is a vector quantity, meaning it has both magnitude and direction. So not only does it tell us how fast the velocity is changing, but also in which direction. Now, in cases of non-uniform motion, the velocity isn't constant. It varies with time. That means the change in velocity isn't zero. It's something we need to pay attention to. And finally, we denote acceleration simply as understanding how acceleration works helps us analyze real-world motion, from cars speeding up on the highway to objects falling under gravity. It's a fundamental concept that connects directly to the overall theme of motion and change. Now let's take a closer look at the distance time graph, which is a powerful way to visualize motion. Essentially, This graph shows us how far an object has traveled over a certain period of time. Think of it as a simple line graph where we plot distance against time to see how an object's position changes. Notice that the distance is plotted on the y-axis, which is the vertical axis, and the time is on the x-axis, the horizontal axis. This setup allows us to easily see at a glance how quickly or slowly an object is moving based on the shape of the line. For example, a straight, diagonal line indicates constant speed, while a curve might suggest acceleration or deceleration. By analyzing these graphs, we can gain insights into the motion patterns of objects in a very clear and straightforward way. This is a fundamental tool because it connects the physical movement we observe with a visual representation, making it easier to understand and analyze different types of motion. So, to sum up what we've learned, if the distance-time graph is a straight line, that indicates the motion is uniform. In other words, the object is moving at a constant speed. And remember, if you're given a distance-time graph for any object, you can find its speed simply by calculating the slope of that graph. The steeper the slope, the higher the speed. Another important thing is that the slope of a straight-line graph remains the same no matter which interval you choose. This consistency shows us that the speed of an object moving uniformly doesn't change. It stays constant throughout. These points really tie back to the overall idea that understanding the shape and slope of these graphs helps us grasp the nature of motion, especially uniform motion. Thank you for your attention. If you have any questions, please feel free to contact me at arthism2003@yahoo.in. Now, let's quickly review the key points about velocity time graphs. These graphs are essential because they illustrate how an object's velocity changes over time. The slope of the graph is particularly important because it represents acceleration, so a steeper slope means higher acceleration. Additionally, the area under the curve tells us about displacement, which is how far an object has traveled during a specific time interval. Understanding these concepts helps us interpret motion more intuitively and connects all the ideas we've discussed about kinematics. Thanks again for your time.